La República de Panama, or Panama, lies in the heart of Latin America. It is widely known for the canal that was built between 1904 and 1914, which passes through the country and divides the American continent. Panama has a fast-growing economy and a large per capita consumer in Central America. Business and investment is very strong. Because of this, it has seen a major increase in its economy and job growth. As a result, a major problem has developed in its daily traffic on its roadways. The problem in Panama City lies on the Corredor Sur, a major highway that goes through the city which many residents use on a daily basis to get to and from work. Originally, it was designed for a travel time of around 15 to 20 minutes from the Tucuman region to the Central Business District. Currently, the peak travel time can be around an hour, while off-peak travel time can be up to 40 minutes. This resident, commuting to work, complains about the rise in toll, the loss of productivity, the money and gasoline spent, as well as the long time it takes him to get to his destination. The solution is a public mass transit system that will utilize the adjacent water surface of the Pacific Ocean to create a transit network that is fast, efficient, and that will alleviate traffic on the Corredor Sur.
The first thing that we had to do was determining the amount of people that will use the ferry system. The method used to determine the travel demand was by analyzing the traffic flow of the Corredor Sur Trust. We found a traffic data done from 2002 to 2004. This data studied the traffic flow by vehicle category, cars per head, origins and destinations, trip purpose, and trip frequencies. In this study, information of the traffic flow was forecasted until the year 2029. After going over the study, we decided that we wanted to decrease the traffic flow of the Corredor Sur Trust by 40%. So after gathering the information needed, we were able to determine the number of people that would use the ferry for their journey. We estimated that about 727 riders in Tucuman, 1,399 in San Francisco, and 392 in San Felipe will use the ferry system transportation. Determining the vessel type to be used was the next step. To do this, we researched different types of vessels that are available. Examples of vessels that may be used to transport people are monohull, catamarans, hydrofoils, and hovercraft. Each have their own pros and cons. For monohull, they have low capital cost and are low maintenance, but the draft is high for shallow waters. Catamarans have a more stable platform than the monohull and is also greater in maneuverability as well. But these boats' capital costs are higher, and at low speeds the fuel consumptions increase, which makes it costly. Hydrofoils are high-speed boats and have a low fuel usage, but they require deep drafts. Hovercrafts work well in shallow areas and high speed, but they have a high capital and maintenance cost, and they are very bumpy, and the exterior noise is very high. After we have determined the number of people that may use the ferry, our next step will be sizing our vessel based on the passenger capacity. We also took into consideration of the distance between our 3 docks and of course the speed of the boat. Based on these 3 criteria, we worked out our options and decided to use a passenger boat with a capacity of 250 passengers and a speed of 25 knots. For the parking lot, we have designed spaces for 923 vehicles total. This also includes 18 handicap spaces. We decided to have a 90-degree parking stall so that it can accommodate more cars. This parking lot is designed on the causeway to make it easily accessible for the commuters to use the ferry. We have selected routes to and from each locations. One route between Tocumen and San Francisco, another one between San Francisco and San Felipe, and a third one between Tocumen and San Felipe.
The geotechnical aspects being presented for this report are two alternatives to make the water transportation system operation possible, and the design of adequate foundations for the pier structures. Alternative 1 consists on building piers on the shoreline. After careful analysis of nautical charts produced by the National Oceanic and Atmospheric Administration, it was determined that the existing conditions do not allow for the operation of water vessels due to shallow depths that extend all along the bay. The solution is to dredge navigation channels that can accommodate two-way vessel traffic, as well as account for the draft of vessels proposed for this project. This means that the channels will have a depth of 5 meters. One way to provide these navigation channels would be to dredge along the length of the bay. It is estimated that close to 4 million cubic meters of material would need to be removed. A second way to provide navigation channels is to dredge paths that are perpendicular to each of the 3 pier sites. The channels would extend into the ocean until the desired depth of 5 meters is reached. It is estimated that over 2.5 million cubic meters of material would need to be removed. A third way to provide navigable conditions is to dredge the entire area in front of the bay until a uniform depth of 5 meters is created. If the previously mentioned dredging volume sounded very large, the material to be removed for this option is sure to sound excessive. In addition, all navigation channels need maintenance due to movement of currents. Alternative 2 consists on building the piers at the end of causeways that would extend from the shoreline of the 3 locations to a distance into the ocean where the desired depth of 5 meters is reached. A causeway is a raised road or path structure that runs across a body of water. This structure would provide the needed navigation conditions that most water vessels need without the excessive dredging and its maintenance. Causeways are built from several compositions that include large rock sizes on the outside for structure protection and varying soil layers inside the structure, which are designed with proper filter criteria to avoid the particle migration produced by the currents. Geotextiles are also popular and serve the same purpose. Due to the strength of large rocks and their abundance coming from the Panama Canal expansion, specifically from the Gaylord Cut area, a causeway composed of only large rocks is recommended. The pier structures would be resting on 10 closed-ended steel pipe piles measuring 0.61 meters in diameter and 40 meters in length. The piles would be driven 28.6 meters into a soil profile that includes sensitive clays, silty sands, sandy silts, and silty clays. The remaining 11.4 meters is the distance from the ocean bed to the concrete girder as specified by the structural engineer. After comparing different pile materials and construction methods, it was determined that the driven closed-ended steel pipe piles are the foundation of choice due to their wide availability, practicality in transportation to the construction site, and high compressive, tensile, and flexural strength. This foundation design provides a factor of safety of at least 2.5. Corrosion protection would be implemented by encircling the piles with polyvinyl chloride wraps that provide a tight-fitting, smooth, wrinkle-free encasement that creates a hermetic seal around the piles.
In the design process, all available specific literature, including International Building Code, ASCE 7, and designer guides and handbooks, were extensively utilized. Various materials were used for this project. 5000 psi concrete and 60 ksi epoxy-coated rebar were utilized to better withstand severe marine environments. Structural steel has a yield strength of 50 ksi. Structure was designed to withstand dead and live loads, wind load, earthquake load, in addition to current load. The pier's gravity load supporting system consists of piles, reinforced concrete girders, beams which rest on the girders, and slab. The roof structure is made out of structural steel W sections and covered with corrugated metal sheet. Railing consists of aluminum pipes bended and connected together to create a dependable barrier. Floating dock and gangway were utilized in order to board and unload passengers from the boat. It is due to high tidal variation. For the accurate analysis of the pier structure, SEP 2000 model was created. This model accurately represents the real structure. It includes the correct sections and properties for steel beams and columns, concrete girders, beams and slabs. SEP 2000 computer analysis provides all the moment and shear forces in addition to the deflections that act on the structure. All is done for the load values and combinations provided by the designer. SEP analysis is very accurate, fast and comprehensive, which is vital for the designer.
Construction of our design will consist of three main phases: creating the artificial causeway, paving the road and parking lot, and finally building the concrete pier. For the causeway, the rock will be taken from the Culebra cut section of the Panama Canal, which is also known as the Gaillard section. Due to the high volume of material needed, which is approximately 369,000 meters cubed, it will have to be transported by barge. The pier's main components consist of 10 ASTM standard A36 mild steel piping used for the piles. It also consists of 5 girders, each with the approximate volume of 250 feet cubed, 24 beams, each with the approximate volume of 62.5 feet cubed, and the concrete slab, which is divided into 4, each section consisting of approximate 625 feet cubed. A total approximate volume of concrete is 5,250 feet cubed.
Numerous benefits which the new water public transportation system has to offer. I would like to name the main ones. First, enhanced personal opportunities for the users. Second, improvement of the traffic situation in the city of Panama. Third, saving time for the system's users. Fourth, minimization of the wasted fuel in traffic. Fifth, preservation of the people's health. Sixth, generation of new employment. Seventh, gasoline consumption reduction. The main social objection that our project can face is that some community members will question the fact that public money are spent on a water transportation system rather than on a new road, highway or dedicated bus route. There is a way to address this issue. The massive public awareness program must be implemented explaining the benefits, capabilities and costs of the new system. The main cultural objection to our project is a cult of automobile. Some residents of the Panama City follow this cultural phenomenon and believe that an automobile is more than just a transportation machine. For them, it is a source of personal freedom, social status symbol, and a way to get to all the pleasure sources that contemporary city has to offer. The best way to address this issue is an appeal to the preservation of the environment and architectural face of the city, as well as the faultiness of the car cult.
There are numerous environmental considerations that come with most construction projects. Marine structures are certainly no exception. The Environmental Impact Statement is an important document in the U.S. which identifies the biotic and abiotic effects that projects produce. A document equivalent to this one is recommended for this project. The following are issues that could be a concern for locals in Panama City. Number 1, the possibility of using contaminated rockfill to build a causeway. In this case, the material comes from the Gaillard Cut, which is an area that is natural and free of industrial pollutants. Number 2, effect on current patterns and sediment flow. Number 3, effect on water salinity and its effects on marine life. Number 4, effect on water temperature. Number 5, pollution produced by the vessels used in the transportation system. Number 6, littering from transportation system passengers. Number 7, air pollution emitted from transportation system vessels. Number 8, possible presence of endangered species. And number 9, effect on marine life in surrounding areas. Mitigation measures include meeting with the pertinent local federal environmental agency to be aware of rules and regulations, and working with knowledgeable staff such as physical oceanographers and restoration ecologists.